this is Saritha, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering. Today's session I am going to explain about the definitions and terminology on Module 2. Module 2 is image transforms. So in this module we are having 2D FFT properties, fast Fourier transform properties, and based on the properties we are having number of transforms are there: Walsh transform, Hadamard transform, discrete cosine transform, Haar transform, slant transform, and Hotelling transform. So in this two-dimensional fast Fourier transform, so what are the properties involved in this 2D FFTs? So we are having separability, translation, rotation, periodicity and complex conjugate, rotation, distributivity property, scaling property. So in this, what is meant by separability? First, consider any image we are representing with f of x comma y. F of x comma y, x and y. This is the image representation. If we are applying the transformation function on this image here, transformation function of f of x comma y, the resultant is f of u comma v, f of u comma v. So it is nothing but f of x comma y is nothing but two-dimensional. So in separable property, first apply the separability on 2D can be divided into two 1Ds. It is 1D, 1D. So here f of x comma y, apply the separable property. For this case, first apply the separable property on x, afterwards apply the property on y. First is f of x comma y. Here apply the separable property. So in this separable property, x domain converted into u domain. So what is the output here? F of u comma y, f of u comma y. Next, apply the separable property on y. Here the input is f of u comma y. Here convert y domain to v domain. Here the output is f of u comma v, f of u comma v. So this is nothing but separable property. So based on this separable property, we are having Walsh transform, Hadamard transform, and Haar transform, slant transform. So in this, first we are applying here f of x comma y, x, y. So we are applying the separable property here. This one is u, here it is y only. Again apply the separable property on y. So here v, here it is u. So here f of u comma v. So f of x comma y is our input image. We are applying the transformation function. Then output we are representing here f of x comma y. Here we are applying the transformation property. Output is f of u comma v, f of u comma v. So what is mean by translation? So translation property means here f of x comma y, we are applying the transformation function. Here it is f of u comma v. So in this translation property, u minus u naught comma v minus v naught. It is the translation property. What is mean by rotation? Here rotation is nothing but the image is rotates. Here f of x comma y, x, y, we are applying the transformation function. Here it is f of u comma v. It is input. We are applying the rotation property. The image is rotates some angle. Here f of r comma r plus theta. So depending on theta, the image is rotates either 45 degrees or minus 45 degrees. So we are applying the rotation property. Depending on application, image is rotates a vertical, horizontal, or some clockwise or anti-clockwise direction. And periodicity and complex conjugate. So periodicity is nothing but here f of u plus n comma v plus n. So here u plus 2n comma v plus 2n. So it is periodicity property and distributivity property. So distributivity property means here f of x, f1, f1 of x comma y plus f2 of x comma y. So we are applying the distributive property here, f of f1 of x comma y plus f of f2 of x comma y. So here f of f1 of x comma y plus f2 of x comma y, it is equal to the f of f1 of x comma y plus Fourier transform of f2 of x comma y. So in here f of f1 of x comma y into f2 of x comma y, it is not equal to f1 of x comma y into f2 of x comma y. So this is distributive property. And scaling property, in scaling property we are representing a f of x comma y, which is equal to the a f of u comma v, a f of u comma v. And here next convolution property. So in this convolution property we are representing here f of x comma y convoluted with g of x comma y. Then here we are representing f of u comma v into capital G of u comma v. For example, f of u comma v, f of x comma y into g of x comma y, which is equal to the f of u comma v convolution with g of u comma v. So these are the properties involved in our Fourier transform. First one is separability, translation, rotation, periodicity and complex conjugate, and distributivity property, scaling and convolution. And in this, what is the necessity of why we go for image transforms? So generally image transforms representation in a 3 or 2 reasons for transforming image from one representation to another representation. So here image in generally we are representing with f of x comma y, but when we go for in a frequency domain or we are applying the transformation function, that image we are representing with f of u comma v. So first the transformation may isolate critical components of the entire image. So for that case we can easily accessible for the analysis. And second property, so why we go for image transforms means first we can isolate the critical components of the image pattern, and with this the isolation of critical components of the image pattern, with this we can easily accessible for analysis. And second one is the image data is more compact form so that they can be stored, transmitted efficiently. So with the use of transformation, the f of x comma y can be converted into f of u comma v. So after the transformation we can easily analyze the image and we can easily transmit the information, and storage purpose is also very easy. And here first one, what is spatial domain? So the section of real plane spanned by the coordinates of an image is called the spatial domain. So in this we are having spatial domain and frequency domain is there. So in spatial domain we are used for real plane spanned. And what is mean by contrast? So if we are considering image, the image is represented in digital form. In that we are having each pixel has its different gray level. So contrast is nothing but which pixel values are having high gray level value, so it is more bright, the contrast is increased, and which pixel values are having less gray level value, the contrast is decreased. Here the difference is intensity between highest and lowest intensity level in an image is contrast. So based on this contrast, so image quality, when we go for histogram processing, this contrast level, low contrast and high contrast, depending on gray level, how many number of bits we are using in each pixel. Based on that, we will decide the image it is in high contrast or low contrast. If number of samples are increased, quantization levels are increased, then number of bits in each pixel increased, then gray level value is also increased. The gray level value is more, the image quality is also good. If the gray level value is less, means the image is somewhat dark compared to higher gray level value. And specify the objective of image enhancement technique. So in this image enhancement, so first we can go for image acquisition, and afterwards we can go for image transforms. In that image acquisition, we are using different types of sensors and digital camera. With the use of sensor, we can capture the image. That image we can convert it into analog to digital form. Then afterwards, we are applying the image transforms. With the use of that image transforms, we can convert it into f of x comma y into f of u comma v. And after, we are using image enhancement. So with the image enhancement, it increases the picture quality. So in this image enhancement, after resultant, we are applying the image enhancement technique on particular image. The resultant image is more suitable for specific application, better than the original image. So in this image enhancement technique, it is the process and image, so that the result is more suitable than the original image for a particular application. So for this image enhancement, we are having different types of techniques are there. So based on our requirement, we are applying any one of the technique. And here in this, to increase the contrast of an image, we are having different types of filters are there. And histogram technique, with the use of histogram technique, we can increase the image quality. And define additivity. So here additivity is nothing but here the property indicating that the output of linear operation due to sum of two inputs is same as performing the operation on the two inputs individually. So here this property is nothing but, for example, f of x comma y. So consider two images, adding of these two is nothing but additivity property. So define categories of image enhancement. So here, direct manipulation of picture image in frequency domain methods based on modifying image by Fourier transform. Here, direct manipulation of picture image. So in direct manipulation of picture image, we are applying the mask. So we are applying the mask. Mask size is always, we are preferring 3x3 mask or 5x5 mask. So if you are applying this mask on particular image, the resultant stored in the center of the pixel only. If for example in 3x3 mask, the total pixels are in 3x3, the matrix size is 3x3, here it is 9. So whatever we are applying this mask to in our sub image, the resultant stored in center pixel, that resultant is stored in this location. So this is direct manipulation of the picture image. And another one is frequency domain methods based on modifying the image Fourier transform. So frequency domain methods, in this we are using different types of image transforms we are applying. Based on that, we can increase the image quality. And next one is write about separability property. So in this separability property, in two-dimensional, consider here f of x comma y, here x and y, this is image. We are representing here it is f of x comma y. So in this separable property, can be 1D analysis in the x direction and 1D analysis in the y direction. So first apply the separable property in x direction, and next apply the separable property on y direction. So it is 1D. So first apply the separable property on x. Then here f of x comma y converted into x domain to u domain. Then output is f of u comma y. f of u comma y. Again apply the same property here, f of u comma y, here y domain to v domain. Then the resultant is f of u comma v. Here the resultant is f of u comma v. So the 2D analysis formula can be written as a 1D analysis in the x direction followed by 1D analysis in the y direction. And what is contrast stretching? So in this contrast stretching reduces an image of higher contrast than the original by darkening the levels. Here higher contrast level means the gray level values are maximum. Here darkening the levels below M and brightening the levels above the M means here contrast stretching means whose pixels are having less gray level value. Here original image darkening the levels below the M and brightening the levels above the M in the image. So in this first consider one level that is representing with M whose gray level value, first assigning the threshold value, that is we are representing here M whose pixel values are less than this M, we can darkening the levels. So whose pixel values are greater than M, we can increase the gray level value. Means if your gray level values are increased, then the image is more brighter. So define mask mode radiography. Here mask is nothing but if image is the size is 256 means 250 rows 256 into 256 or 8 by 8 matrix. 8 by 8 matrix. In this 8 by 8 matrix, we are having total 64 pixels only. So in that entire image, I need to I need to change this pixel value only. So it is 3 by 3 mask. It is 3 by 3. This is we are representing as a sub image. So sub image. So apply the 3 by 3 mask. Apply the 3 by 3 mask onto this original image. So whatever the resultant is there, either we are multiplying the original sub-image pixel into mask pixel or subtracting the value that resultant stored in center of the pixel. So here in commercial use of image subtraction is called mask mode radiography. And what is gray level slicing? So in this gray level slicing, so here the gray levels are we are considering in, so this is one level, here it is in one level, here it is in maximum level. So with the use of gray level, highlighting a specific range of gray levels in an image is called gray level scaling. So in this from here to here, we are representing some area 0 to A. From here to here it is A to B. Here to here B to some maximum. This area is maximum gray level value. So with the use of gray level slicing, first one the level is very low and next criteria here it is A to B. And last one it reaches to the maximum gray level value. So here gray levels are, we are representing 0 to L minus 1, 0 to L minus 1. L equals to 2 power K, K is nothing but number of bits. K equals to number of bits. So L equals to 2 power K means, for example, if we are using K equal to 8 bits. If you are using 8 bits in each pixel, then L equals to 2 power 8. Then here it is 2 power 8 means here 256. What is the gray level? Here 0 to 256 minus 1. So the gray level value we are representing here 0 to 255. Here 0 is the minimum gray level. Here 0 is the minimum gray level. And 255 is the maximum gray level. Here 0 is the minimum gray level, 255 is the maximum gray level. So in this condition we are having total 255 shades. In this we are having total 255 shades. So in that image, some pixels are some gray color, some are dark, some pixels are in bright level. So total in this we are having 255 shades. So this is nothing but a gray level. So in our image representation, we are having different types of representations are there. Gray level representation, binary representation. So here binary means we are going to represent either 0 or 1. 0 is the maximum gray level. Maximum gray level. Sorry. 0 is the minimum gray level. So in that we are having in binary, the represent a image in binary form means in that we are having only two variations. One is black and one color is white. So black and white only. So it is nothing but binary. So binary we are representing only two bits, 0 and 1. 0 is the black representation means minimum gray level, and here 1 is the white means maximum gray level value. So how to, for example, the image it is in the form of some gray level. So how to convert that image into binary form means here consider threshold value. Consider threshold value based on the threshold value whose pixel values are based on the threshold value whose pixel values are greater than that value, then represent with 1, and below that value then represent with 0. So based on that, gray level image can be represented in the binary form also. And define masking. So region of interest here operation is commonly called masking. So region of interest is nothing but already I explained here mask. Image size is 256 into 256. So entire this image I need to change only particular pixel only. So I need in this portion. So for this case, in this portion, consider it is a 3 by 3 sub image, the sub image. So 256 into 256 is our main image. So in that, I need to change the value of in particular pixel. For that case, the total divide into sub this entire image. No need to consider this entire image. Just consider sub image of this main image. So sub image size is, for example, here it is 3 by 3. So apply the same mask. So apply the 3 by 3 mask onto this image. It is nothing but region of interest operations. Region of interest operation means I need to change the gray level value or properties of my image in this portion only. For example, I need to change the properties of original image in this portion only. So based on our interest, apply the mask on particular sub-image only. So this is nothing but region of interest operation is commonly called as masking. And define image subtraction. So define image subtraction means the difference between two images. So difference between two images. So how to do the subtraction means depending on our requirement, subtract the gray level values. So here next question is define Walsh transform. So in this Walsh transform, here the what is the cardinal equation for Walsh transform? Here g of x comma u equals to 1 by n pi I equals to 0 to n minus 1 minus 1 power b I of x bn minus 1 minus I of u. This is a Walsh transform. So this Walsh transform is an orthogonal transformation and decomposes a signal into a set of orthogonals. A rectangular waveform is called Walsh transform. So in this, with the use of this Walsh transform, depending on n. So depending on n, if n equals to 8, the how many computations we need to calculate? Total 64 computations. Here the mask size in a rectangular form. Here we need to calculate total 64 computations. Here 64 computations means here 2 power 3 equals to 8. So here I value varies from 0, 1, 2. So substitute here I value 0 to, so I value 0 to n minus 1. So 0 to 3, 0 to 3, 0 to 3, I equals to 0, and what is the value? I equals to 1, what is the value? I equals to 2, what is the value? That is power of minus 1 power b I of x, b n minus 1 minus I of u. So based on this kernel equation, this is the Walsh transform 1D kernel. Based on this kernel equation, find out the total computation. So Walsh transform is nothing but it is a orthogonal transformation that decomposes a signal into a set of orthogonal or rectangular waveform is called a Walsh transform. Here, after calculating of these computations, here represent depending on values, depending on coefficients. Here the coefficients are total 64 coefficients. So the 64 coefficients represent in the form of waveform only. If it is 1, represent in high level. If it is minus 1, represent with low level. So here the coefficients all are between 1, 9 minus 1 only. 1, 9 minus 1 only. So based on this, represent in a rectangular waveforms. So this is the 1D kernel of Walsh transform. So when we go for 2D kernel, g of x comma u comma y comma v equals to 1 by n, I equals to 0 to n minus 1 here, minus 1 power b I of x, b n minus 1 minus I of u, plus b I of u, b n minus 1 minus I of y. Here y, here it is v. So g of x comma u comma y comma v equals to, it is the 2D kernel of Walsh transform. This one is 1D kernel of the Walsh transform. Here it is 1 by n summation I equals to 0 to n minus 1 minus 1 power b I of x, b n minus 1 minus I of u, plus b I of y, b n minus 1 minus I of v. So this is the 2D kernel of the Walsh transform. What is image averaging? So in this image, with the use of this image averaging, so for example, the image size is 3 by 3. Add all the pixels divided by with 9. So 3 by 3 means total number of pixels are 9 only. So sum of all the pixel values divided by 9. It is nothing but averaging of image. So with the use of this average image, the image going to get blurred. The mask size is increased and image clarity is decreased. So image averaging technique is basically used in image enhancement that have been corrupted by random noise. Corrupted by random noise means mask size is increased, then image quality is decreased, means the video images that have been corrupted by random noise. And define image multiplication. So image multiplication means the first form takes two images and produces output image in which pixel values are just those of the first image multiplied with the same corresponding pixel values of the second image. For example, here this is one image, this is image 1, this is image 2, this is image 2. So here image multiplication means this pixel value multiply with this pixel value. This pixel value multiply with this pixel value. This pixel value multiply with this pixel value. So the output of the first form takes two input images and produces an output image in which pixel values are just those of the first image multiplied by the values of the corresponding values in the second image. So here this is the first location, multiply with the first pixel of the second image. So like that, multiply the two images, that resultant is stored in same location only. What is mean by masking? So mask is the small 2D array in which the values of mask coefficient determines the nature of process. So depending on our requirement, here mask we are representing W1, W2, W3, W4, 5, 6, 7, W8, W9. So this is mask. Here subimage we are representing Z1, Z2, Z3, Z4, Z5, Z6, Z7, Z8, Z9. So this is subimage. This is the filter mask. So we are applying the subimage on each and every pixel of we are applying the filter mask of each and every pixel of this subimage. Then output is Z1 into W1 plus Z2 into W2 plus Z3 into W3 plus Z4 into W4 plus Z5 into W5 plus Z6 into W6 plus Z7 into W7, Z8 into W8. Whatever the resultant is there, that resultant is stored in our Z5 location. Define single pixel operation. So here the procedure is done on a digital image to alter the values of its individual pixels. And next one, define histogram. Histogram is a digital image with gray levels in the range. With the gray levels in the range. In this histogram is nothing but the image is represented in the digital form only. So with gray levels in the range only. So define type point. So geometric spatial transform points whose locations are known as type points of an image. Define sine wave. So sine wave is nothing but when we are representing image, it is in continuous form. It is in sine wave. Afterwards, we are applying the sampling and quantization. We are representing in pixels only. So what is a median filter? So in this median filter, whatever the pixel values are there, that pixel values are arranged in a ascending order. From that, find out the middle value. It is nothing but median value. The median filter replaces the values of a pixel by the median of the gray levels in the neighborhood of the pixels. And what is soft X-rays? So soft X-rays or low energy are used for dental and chest scan. So what is soft X-rays are nothing but these rays are low energy are used for dental and chest scans. So name of the different types of derivative filters. So in this we are having different types of derivative filters. We are representing with dou f by dou x and dou f by dou y. So with the use of x and y, it scans the vertical lines and horizontal lines of an image, and it scans the plus 45 degrees and minus 45 degrees. So here in this we are using Prewitt operators, Robert Cross gradient operators, Sobel operators. So here different types of derivative filters are there. Prewitt, Robert, Sobel filter. So mostly we are using Sobel operators to scan the vertical, horizontal and plus for inclined lines also with the use of this Sobel operator. So in that depending on mask, so I need to scan the vertical lines or horizontal lines are plus 45 or minus 45 degrees based on mask, whatever the values in given in our mask. Here the So here the Sobel operator or Robert or Prewitt kernel, the masks are sum of all the pixel values are equal to the 0. Sum of all the pixel values are equal to the 0 means it maintains the constant intensity value. So based on that we can easily detect the vertical horizontal lines of an image. Define brightness. Brightness is a subjective descriptor, light perception that is impossible to measure. And what are the types of noise modules? Gaussian noise, relay noise, Erlog noise, exponential noise, uniform noise and impulse noise. So when we go for in image processing, we are having different types of noise. Impulse noises means it is sudden changes in our images. Sudden changes are images. For example, step change. So step change means up to some level is same gray level. Suddenly it changes the gray level value. Filter. So filter, with the use of filter we can remove the unwanted noise of an image. What is monochromatic light? So light is a single wavelength is known as a monochromatic light. What are brightness bodies? Here, brightness embodies chromatic notion of intensity and is a key factor describing the color sensation. What is smoothing filter? So with the use of smoothing filter, we are using low pass filter. So with the use of low pass filter, it gives the smoothing of an image, and noise reduction is obtained by blurring the image using smoothing filter. So when we are applying the low pass filter, the output of image is smooth, but image gets blurred. What is average of pixel? So the output of response of a smoothing linear spatial filter is simply the average of the pixels contained in the neighborhood of the filter mask. So average of pixels means here, in this the pixel values are representing for example 1, 3, 5, 7, 8, 10, 12, 13, 15. Sum of all the pixels. So sum of all the pixels divided by with 9, it is nothing but average of filter. So with the use of this average filter, the output is out brightness of the output is decreased. Means the mask here, the filter size is here, it is 3 by 3. For example, increase here, it is 5 by 5. Image is not clear. So it is nothing but a random noise occurred when we are using this average filter. In our image, some noise is introduced. And what is smoothing and linear spatial filters? So smoothing linear spatial filters is the average of the pixels contained in the neighborhood of the filter mask. So here average filter or smoothing filter or low pass filter, three are similar here. So with the use of smoothing filter or low pass filter or average filters, the output of the image is smoothing but not clear. So smoothing the spatial filter from the average of the pixel is called the averaging filter. Define sharp transition of gray level. So sharp transition of gray levels means here the gray level value up to is 0 to 255. For example, if we are using L equals to 2 power k. In this k equals to 8 bits. L equals to 256. So the range of gray level 0 to 255. So up to here it's some level. Suddenly it changes its range. So suddenly changes means up to here the gray level value, for example, consider 0 only. Suddenly it reaches to the 255 gray level means suddenly changes from dark to white. So smoothing filter replaces the value of every pixel in an image by the average value of the gray levels. So this helps is removing the sharp transition in the gray level between the pixels. So here in this it changes from 0 level to 255 means suddenly changes from dark to white. So with the use of this transition, with the use of this sharp transition means gradually increases the gray level from 0 to 255, some 0, next 126, next 64 or 128. So like that it increases the gray level values linearly. And define blur edges. So edges is almost always desirable features of an image, also characterized by sharp transition in a gray level. So how to sharpening of edges means, for that case we are using high pass filters. So with the use of high pass filter, it gives the sharpening of an edges. Sharpening of an edges. Low pass filter is nothing but smoothing of an image. And what is the disadvantages of using smoothing filter? So the disadvantage using smoothing filter is blur the edges. So with the use of high pass filter, sharpening of an edges. With the use of smoothing filter is nothing but low pass filter. With the use of low pass filter only, we'll get image smoothing, but edges are blurred. And define smoothing filter. Smoothing filters are used for blurring and noise reduction in the image. Define sharpening filters. Sharpening filters can be help emphasize details in and enhance the edges of object of an image. Define box filter. So a spatial averaging filter or spatial smoothing filter in which all the coefficients are equal is also called as box filter. So spatial averaging filter or spatial smoothing filter in which all the pixel or here all the coefficients or pixel values are equal is called the box filter. And write about a Hotelling transform. So here the Hotelling transform is a linear transformation of a set of n-dimensional vectors so that correlates n coordinates. And write about Hart transform. So in this Hart transform is used for image compression. The basic idea in this transformation, here we are representing in this Hart transform hk of z. If k equals to 0, any value of z, we are representing the coefficient value is 1 by root n only. 1 by root n only. So other than this, if k equals to not k equals to some value 1 or 2. So for that case, we can go for some characteristic equation. That characteristic equation is hk of z equals to 2 power p by 2. Here q minus 1 by 2 power p less than or equals to z less than q minus 0.5 by 2 power p. Here minus 2 power p by 2, here q minus 0.5 by 2 power p less than or equals to z less than q by 2 power p. In otherwise 0 only. Here hk of z, if k equals to 0 any value of z, we are representing the coefficient value is 1 by root n. Otherwise, if the z value between these limit q minus 1 to 2 power p less than or equals to z less than q minus 0.5 by 2 power p, if z value between these two, then we need to consider the coefficient value is 1 by root n into 2 power p by 2. If the z value between 0.5 to 1, at that time we need to consider the coefficient value 1 by root n into minus 2 power p by 2. Otherwise, we need to consider 0 only. So this is the Hart transform. So in this Hart transform, the basic idea is it is basically used for image transform in which each element of the matrix represents a pixel in the image. What is a nonlinear smoothing filter? So order statistic filter or nonlinear smoothing spatial filters whose response is based on the ordering or ranking on the pixels. So up to here, these are the definitions of in our second module, that is image transforms. So in this image transforms, the basic topics are 2D properties and transforms. So properties are separable, translation, rotation, convolution, distributivity property, and transforms are Walsh transform, Hart transform, Hadamard transform, slant transform, and Hotelling transform. So in this we are having different types of transforms and properties and some filtering techniques and how to do the enhancement and what are the filters we are using to remove the noise components and what is mean by gray level and how to apply the transforms on our images. So these are the basic definitions in our second module, image transforms. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.